Hello, this is Lab 5, the final lab of Physics 2211. Christoph Hammel is a professional trampoline jumper who performs a lot of amazing stunts. For this lab, I analyzed his motion in one of his jumps, where he fell off a high platform onto a trampoline and then bounced back onto the platform. With various equations, I proved that his energy remained constant throughout the stunt. This conservation of energy and the methods that I used can be applied to other objects as well, whether they're falling, bouncing, or moving in some way where there are changes in the types of energy. Here is the video of his motion imported into Tracker. On Canvas, we were asked if Christoph had discovered a way to violate conservation of energy. Obviously, the answer is no. The law of conservation of energy is true for every system and its surroundings and can never be broken. This can be proved mathematically in a few ways. First, we know that the change in energy of a system, in this case Christoph, is equal to the work done on it. Work is equal to the component of the net force on the object and the direction of displacement. If Christoph starts and ends at the same position on top of the block, then his total displacement is zero. This means the work, and therefore change in energy, is zero. His delta E between any other 2 points is zero as well. For example, let's take his initial position to be at the top of the block and his final position to be right before he hits the trampoline. At the top, he is motionless, so his kinetic energy is zero. However, he is far above the trampoline, so he has positive gravitational potential energy. At the bottom of his fall, he is moving with a downwards velocity, so he has kinetic energy. However, his potential kinetic energy in relation to the trampoline is zero, because his distance above it is zero. This means that all of the initial potential energy was transformed into final kinetic energy. I made two simulations in GlowScript to model his motion more accurately. This one is for the downwards fall. And this one is for the upwards bounce. As you can see, the graphs for the object's predicted y position versus time is very similar to its measured positions. The differences are because of my inaccurate measurements. I tracked the center of mass of Christoph's body, which is irregular and constantly changing shape. I could not be as precise as finding the center of mass of a ball of constant density, for example. His body was also constantly changing configurations. Sometimes he would be curled into a ball and sometimes he would be stretched out. This made it even harder to find an accurate center of mass. Additionally, there were many forces acting on his body in reality, such as air resistance. I only took gravity into account for the GlowScript model, so it represents a simpler situation. I didn't model Christoph's motion after he hit the trampoline, as that involves an additional force that would have been difficult to code. However, this part of his stunt still follows conservation of energy. When he hits the trampoline, it stretches a little. At its maximum stretch, he is at rest and is below the trampoline's original position. This means that his kinetic energy is zero and his gravitational potential energy is actually negative, as h is negative. The trampoline exerts an upwards force opposite his downwards motion, which causes deceleration. Work is therefore negative, and according to the equation discussed earlier, delta E must also be negative. This matches our observations with the negative potential energy. When he bounces upwards again, the explanation is fairly similar. He starts with a negative total energy, and when he leaves the trampoline, his energy is positive, as he has kinetic energy. This means he has a positive delta E corresponding to the positive work. This balances out with a negative change in energy mentioned earlier, so energy is conserved even during this part of his stunt. As you can see by the energy graphs of Christoph's downwards and upwards motions in GlowScript, his delta E is always zero, meaning that energy is indeed conserved. This can also be proven by observations of his position and velocity. However, in order to reach this conclusion, I needed to make a few assumptions, with the main one being that kinetic and gravitational potential energies are the only types of energy present. In reality, a very small amount of the initial energy was converted to other types, such as thermal and sound. However, using only the information available to me in the video, I was able to describe the motion and energy very accurately. Thank you.